Okay, we have here what's the tractive effort versus longitudinal slip. And again, in here you have the variation of this tractive effort versus longitudinal slip of the tire. And in this case, you have the sliding value, and then you have the peak value. So there are many of these experimental charts that have been made about tires. So tires have a lot, this coefficients, they have a lot to do with these experiments. This is another view now, a little more scientific view of what it is to have a how the tire behaves under a braking torque. And then you can see how things change. Like in this case, you have the tire is moving counterclockwise and the torque is clockwise. So the tire is going to produce the friction force F sub x in there, but you could see how under the braking torque the tire will deform basically on the side, under the brake. The car is going this way, but we're braking the other way. So in here, this would be a plot of the pressure, and this would be of the longitudinal stretch of the tire under that condition. So this is a measure of how that stress is produced by this torque. So you can see in here how this will change. F of x will be the highest close to the edge. Let's move on. Okay, so this slide here shows you the variation of the braking effort coefficient with skid of a car tire for several of the surfaces. So in here you can see this is basically like measuring the coefficient of friction, but see the coefficient between 0.2 and 0.1, there are icy conditions here. So it explains the low number here. This one, say on loose gravel goes up a little bit, and then on dry conditions you can get the highest torque. So based on this, you see that the bias plate tire is actually good for braking. I see those used in tow trucks and buses. And you can see this is This is why, because they can also be very efficient in braking. This is the measure or an experiment of the braking effort versus the inflation pressure. So let's talk a little bit about this. This is the inflation pressure. These are this normal. My vehicles are around 35 pounds in here. So these are the peak and the sliding values for the braking effort. So you can see the sliding is down there, and this is the peak braking coefficient. On this right hand side is for the radial tire. I think one thing that we can conclude is the bias belted tire and radial there's not much of a difference in this case with the different tires. So this is the sliding values of braking effort with inflation pressure. Okay. This is also a measure of the coefficient of road adhesion. Has to do also with the resistance of the tire to turning. Here are some interesting data so that you begin having in your mind the value of this coefficient of road adhesion is for asphalt concrete 0.75. So whenever we can get a coefficient of friction above 0.6 or 0.7, we're doing really good. If the surface is wet in asphalt, it goes from 0.5 to 0.7. And then concrete and concrete 0.8, which is concrete is actually good for braking. Gravel 0.6 and 0.55. Then you have earth road dry 0.68, earth road wet 0.2, and ice 0.1. So anything that closest to about 0.1 is bad news. I think that would be one of the messages that I would like you to take away from this lecture is that any coefficient of friction, particularly below 0.2 and close to 0.1, the handling is not good. It's very slippery. this is also important to look at, because this slide talks about the speed on braking performance. Okay, so we have to specify several parameters, like in this case, braking of a truck tire on asphalt. Okay, let's take a look. See, braking effort coefficient goes 0.3. No. Which one would be the most efficient? I would say the 10 miles an hour can brake really good. Yeah, so this is a measure of how much it would skid, but I would say that for this you have, I think the one at 10 miles per hour is probably the best. See, 20 miles an hour, 55 you get the lowest braking coefficient. Mm-hmm. This is a chart of the braking effort and how much skid and the weight. So it's got three things. Obviously the skid occurs, 100% skid is here on the right hand side, and you have the braking effort on the left hand side. But you can see that with a 9,000 pound vehicle, it's very easy to skid. Tires have other properties that I think that we need to look at. Cornering properties of tires. Let's talk a little bit about that. Here. This is a realistic view of what happens with when the vehicle is going on on a corner, so you can see the force is going out and the vehicle is coming towards you like this, and this is what happens to the tire on the bottom. But look what happens to the middle. And of course, these are exaggerated a little bit because you don't see this radical deformation unless you have you're taking a curve at 80, 90 miles an hour. But in principle, this is what happens to the tires when you take a corner. Then, okay. This is very interesting because this chart was made with different kinds of tires, some bias and some radial tires. And there's different brands like Goodyear, Super High Miler, Bias Play, has a very high coefficient of friction. If you have like a 0.8, that's probably the maximum you can get. I've never seen it 0.9, but 0.7, 0.8 on tires working on asphalt, that's what you would see. Then General Tire GTX 0.2. You see this one is a radial tire. Firestone transfer. So these are on dry concrete. Michelin 0.7. I always have preferred the Michelin tires, they're really good. And you can see pretty much the average 0.75. But if the condition is wet, I would safely say the variation is like 0.2 to 0.15 more or less, and that's a big loss in traction. So it's no secret that driving in wet conditions, it's bad. Yeah.
What's the difference between the rib and the lug? Is that chart counted? It says Goodyear Super High Miler rib.
I don't remember that. It's more because it would be I would say a rib is normally for radial tire, but this is bias plate, so I really don't know exactly what it means. But this gives you an idea of what the numbers are. This is some cornering characteristics of tires. Like slip angle. Normally a slip angle is about 5 degrees, 5 to 8 degrees.
But what is a slip angle?
Okay, all right. I always have myself trouble with this, but I finally understood this. If the car is going, let's say in this direction, now you decide to turn. Okay? You turn turn the wheels, let's say 20 degrees, just for the sake of example. I see that turns to 10. The car does not go 10 degrees. The car drives 8. This difference is called the slip angle.
Alright, so it's the difference between the angle of the tires
And the actual direction of travel.
Alright.
That's what it is. And you could understand why, because when the tire is turning, there's a motion down like that, and at the same time like this. And it's not precise.
It's not exactly.
Not exactly, but a little bit like 2 or 3 degrees. And that's called the slip angle. And so, so there's a few of this. I'll try to show you a balance of these experiments that have been done and other approaches to this. So I would, this is on the internet. You could take a look at the different things that influence. There's a lot of factors regarding tires, but this one also for tires, you could see that the Michelins are really very efficient tires. They're tricky because just small variations could produce difference in these numbers that would influence the performance of it. So I think that we'll stop now for now. This is just basically an introduction to what tires can do for you on how to measure them. And so